In this video, we're going to be finding extrema in Calc 3. To start off with, we're briefly going to review extrema in Calc 1. Later, we'll move into finding local extrema for Calc 3. And finally, we'll finish with finding absolute extrema. First, we're going to review finding extrema in Calc 1. Here we have a rather interesting sketch of a graph. Here you can see there are a few points of interest. We have a local maxima here, local minima here. And at both of these points, what's important to note is that the derivative across these points changes from positive to negative, and also the derivative at these points is equal to 0. That holds true except for the relative minima, the sign changes from negative to positive. And the derivative again at this point is also 0. However, if you remember, the definition of critical points states that they occur at either points where the derivative is equal to 0, or when they can occur, or when the derivative is undefined. So here we have two sections of the graph where the derivative seems to change. There's not really a concrete value, both of these points at which the derivative is equal to anything really. So as you can see over here, the sign still changes from positive to negative, so this is a relative max, and this is a relative min. But it's important to know when looking at critical points that some critical points are not going to be either. You're going to have some areas like, for example, vertical asymptote where the derivative is undefined, but it may not necessarily be max or min. Also, when you have a flat line of a graph, it might not necessarily be a relative max or min. One way to test a critical point, just from given, is the first derivative test, in which you would, like I explained earlier, just check to see if the sign of the derivative changes across that point. And that's the same thing as saying, across a relative maxima, the derivative would change from positive to negative. Another test is a second derivative test, in which case, this is very similar to the discriminant we'll talk about in a second. We evaluate the second derivative, look at the sign, and from there we can see if it's maybe a relative max or min. And finally, it's important to distinguish between absolute and local extrema, meaning even though necessarily the end of a curve might not be derivative equals 0 or derivative is undefined, but you might have a value, say, towards the end of a curve that's greater than, say, the relative max within the curve, or within the boundary.
So now we will be talking about relative extrema in Calculus 3. So what relative extrema or maximum and minimums are points on a specific interval that are the highest and lowest points in that interval. So if you have a specific area, whichever points are the highest and lowest in that interval are what would be classified as the relative extrema. So there are 5 rules that we will be using to solve this kind of problem. So first, you will find the partial derivative with respect to x and y using the original function that they give. Then you set the partial derivatives equal to 0 and you solve. The solutions found are the critical points. And you plug these critical points back into the function and you find the discriminant, which is basically similar to the second derivative which we talked about earlier. So to find the discriminant, we will be using this equation. So here we have discriminant is equal to the second partial derivative with respect to x times the second partial derivative with respect to y minus the second partial derivative of x with respect to y. So you will use the first partial derivative of x and find the second partial derivative with respect to y, and you would square that. So you would follow these rules to determine if the critical point is an extrema. So these rules, once you solve for the discriminant, you would use these to find if your critical point is a relative minimum, maximum, or saddle point. So if the discriminant is greater than 0, then that would mean your critical point is a minimum or maximum. If your discriminant is less than 0, it is a saddle point, and if it is equal to 0, then your critical point is undefined. An important thing to know is that the saddle point is a stationary point that is not a relative extrema, so it lies flat on the 3D graphs, and we will be showing you a picture. So what we have here is an example in which we will be solving for the relative extrema given a function. So we already solved for the first and second partial derivatives, and we also solved for fxy. If we first set the first partial derivatives equal to 0, and when we do that we get 0, and plugging them back into the original function we get the second point. So we get 0, 0 as one critical point and 1, 1 as our second critical point. Next we use the discriminant function, so we basically just plug in the values into this equation. So the fxx as we found was 6x, and times the fyy, which we found was 6y, minus fxy, which we found was -3, and we square that. So our discriminant equation would be 36xy minus 9. So next we would test each of the critical points inside the discriminant equation to get a discriminant. So plugging in 0, 0 inside this, we would get -9 as the discriminant, and doing the same for 1, 1, we would get 27 as our other discriminant. So now we would use these rules to figure out 0, 0 and 1, 1 as relative extrema. So we'll start with 0, 0. So we have -9, which is less than 0, so that would mean, according to the rule, that it's a saddle point. So 0, 0 is a saddle point. And for 1, 1, we can see that 27 is greater than 0, but that would mean it could either be a minimum or maximum. So we would have to look at the value of plugging in 1, 1 into the fxx. So once we plug in the 1 into fxx, which is 6x, it would be 6 times 1, which is equal to 6, which is also greater than 0. So that would mean 1, 1 as a critical point is a minimum.
Finally, we're going to talk about finding absolute extrema in Calc 3. As you can recall from Calc 1, endpoints of a function are like the actual points in a two-dimensional function. However, in Calc 3, we're going to see how three-dimensional graphs have more, boundaries, you could say, instead of endpoints. Here you can see this paraboloid with a circular boundary. Quickly to define two important terms, open region versus closed region. An open region, is a set of points enclosed by some function, but not including the boundary. A closed region, by contrast, includes this boundary. For absolute, maxima, and minima, we're actually going to look at these boundaries. The general process for evaluating absolute extrema problems is, 1, just like relative, find all the critical points. Second, we're going to evaluate the function at each of these critical points. We don't really have to classify these because we're just looking for the absolute biggest or smallest value, so just a value will do. And something to note is that you might end up having to use intuition. Say if you have a circular boundary, you might have to plug in parts of the equation, or if you have a rectangular boundary, as we'll see in a little, you might have to restrict the domain for a few times to evaluate extrema on these. And finally, pick points that yield the highest and lowest values as either your absolute max or absolute minimum when plugged into fxy. So really quick to discuss one situation that you might encounter is a rectangular boundary. The way to go about solving these problems, or finding absolute maximum minima, is to also test all the critical points within this region and the boundaries. To evaluate the largest and smallest value on these boundaries, simply realize that at this point, say y equals 1, is defined from between the values of x greater than or equal to -1 and 1. From there, you can plug in y equals 1 into the original function, and you'll end up with an equation with one variable. Then it's just a matter of finding the absolute max here. It's a Calc 1 problem, from -1 to 1. You would repeat that for all the boundaries, eventually finding an absolute max or min.